How do we calculate dot products of vectors? So first of all, what is a dot product? Um, why are we calling it a dot product rather than just the product multiplied? Well, vector operations have, we've talked about the first two already, scalar multiplication, when we take a scalar, multiply it by a vector, and it just becomes longer. Or shorter if you're multiplying by something between 0 and 1, or if you multiplied by a negative, it would go in the opposite direction. Vector addition is when we take two vectors and add them together by placing them tail to head, and this is the overall resultant vector. The dot product is what happens when we take two vectors and find out their parallel components and multiply those together. So if we think about this as the parallel component of the part of this vector that is parallel to our other vector, and we multiply this and that together, what is the product of those two things? And the cross product represents when we take two vectors and we look at the perpendicular components. So we're comparing this to the perpendicular component. So this is kind of a weird explanation, but it should make more sense when we start talking about real-world applications and also how to calculate it. It is important to note that the dot product and the cross product have a dot and a cross to symbolize them, and you cannot switch them. So please make sure that when you're calculating a dot product, you use a dot, not an X, to represent the multiplication. So the dot product is an operation that takes in two vectors as inputs and outputs a scalar. So we'll have two vectors, cross them, dot them, and the output will be some sort of number. We can call it D, but it will not be a vector. The dot product means the product of the parallel components. So if I look at this vector and this vector, I can decompose this blue vector into these two green vectors. And then it's a question of what are the product of the parallel components? Well, this green part is not parallel to the red in any way, but this green part is, so we're multiplying those two. The dot product is used in physics to calculate work. Specifically, the definition of work is force dotted with displacement. So it's a very useful term, and you will need to understand it in order to do some of your physics later. So how do we calculate the dot product from component form? If we have something like 2, 3 dotted with 5, negative 2, what do we do? Well, we will multiply the parallel components. Well, 2 and 5 are both x components, so they are parallel, and we will multiply those together, 2 times 5. Also, 3 and negative 2 are parallel components, so we will multiply 3 times negative 2. Now, when we multiply those, we take the sum of each of the parallel component products. So 2 times 5 is 10. 3 times negative 2 is negative 6. So the overall dot product is 4. It is possible to have a dot product that is negative. If a dot product is negative, it means essentially that the vectors are, the parallel parts are going in opposite directions. You can think about this as, this is one direction, but it's being pulled in some other direction. Or we can get a zero dot product if there is no parallel component. So these two vectors are not parallel. Therefore, you should know automatically the dot product has to be 0. If they are completely parallel, then you're just multiplying their magnitudes because 100% of the vectors are parallel. So let's do some practice. Calculate the dot product of these two vectors. Multiply the x components, multiply the y components, and add. So multiply the x components, multiply the y components, and add. Here, I've written it with as a linear combination of unit vectors, we're still going to multiply the I components, so 7 and 1, -4 and +4. This is not the distributive property in any way. We're just multiplying parallel components. So 7 and 1, -4 and +4. And then when we add these, we get -9. So this has a positive dot product. This has a negative dot product. If we are given the magnitude and direction of the vectors, we can look at the dot product in terms of those. So if you look at this diagram, we have two vectors, v and w, and what we tend to talk about is the projection of v onto w. So think of it as what part of v is parallel to w. You'll notice that this w doesn't have to be a horizontal vector in order for us to do this. We can still say, all right, here is the parallel component from v there. This part of the vector is parallel. So how do we calculate that part? Well, if this is v, we say that this is v times cosine of theta because it's the adjacent part of the triangle. It's adjacent to theta. So we're multiplying the parallel parts. We have v cosine theta and w, so we'll multiply those. So we take the magnitude of v, the magnitude of w, and then times cosine of theta. So that is how we calculate it from magnitude and direction only. This is more useful when you see things labeled like this, not with component form. So if you see here, we have the dot product of 28 and 10 with a 40-degree angle between them. That's 28 times 10 times cosine of 40 degrees. It does not matter which one you consider as v or w. It just matters that the angle has to be the angle between them. So 28 times 10 is 280 times the cosine of 40 degrees is approximately 214.5. That is the dot product of those two vectors. Here we have that this is v times w times cosine of the angle between them. And it's always going to be cosine for dot products. So 5 times 6 is 30 times cosine of 145. That is not on the unit circle, so we need a calculator for it. It is negative, it's worth pointing out, and we'll get negative 24.6. So these are the dot products. You'll notice that because these are mostly pulling in opposite directions, you'll see that the dot product is negative. These vectors are mostly parallel, although not completely parallel, which is why it's relatively positive. That's how we calculate dot products.